In our last video, we took our first look at parametric equations. The idea was that the movement of an object is dependent on the time. So we took a look at x and y as both being dependent on the time. And we would create a separate function based on time for both x and y. We're going to go the other direction this time. Suppose we have a parametric equation and we want to get rid of that time aspect. Well, it's pretty straightforward. What we're going to do, sometimes there'll be some trickery to it, but the concept is pretty easy. What we're going to do is we're going to solve, we have these two parametric equations, obviously they go together. The x and y are both dependent on the time. Well, let's solve one of them for t, because if we know what t is in terms of either x or y, we could do a simple substitution. So if you look at these two equations, the easier one would be that we're going to say y equals 2 plus t. Solving for t, we get t is y minus 2. Now let's go to the other equation, the x equation, and where we had t, we're now going to replace that with y minus 2, just that simple substitution. Now you could expand this if you want, multiply that out, and you get down to here. Now, not a typical looking equation. It's in terms with the x on the left, but we could have actually gone either way. You can do this either direction. But we get an equation that has eliminated the aspect of time. We've eliminated that parametric aspect. Okay, so let's do it again here. Let's try to eliminate the parametric aspect of these equations. I think you'd agree the bottom one looks like the easier way to go. So I'm going to solve this for t. I'm going to send t over here, and y over is going to come over here. So this will make that positive t, this will make it negative y. So if this is what t is, I'm now going to substitute that in. X is then 2 negative y. Well, I don't want to write it like that. Let's make this 5 minus y, since we usually like it like that. So I'd have 2 5 minus y squared plus 6. Now this is done. I mean, you don't have to expand it, but you could if you wanted to. I'm just going to leave it here. You could FOIL this out if you know the pattern because you're squaring the same thing, but this is good enough. Okay, now this one is going to follow the same concept, but it's going to be a little trickier. So we're going to start, this is the simpler of the two equations, but seeing the trick we're going to do here is not as intuitive. We're not going to, without using logarithms, which we could, but without using logarithms, look at the switch we've done here. This is the same as x equals 1 over e to the t. Isn't that what a negative exponent does? So he's down on the bottom. So I could switch these around and get e to the t equals 1 over x. Now you say, well, I haven't solved for t, but look at the other equation. The other equation has an et in there, e to the t, so this would be a valid substitution. I know e to the t equals 1 over x, so I could make that change. And I'd have 3 times 1 over x, or 3 over x. And we've done it. We've eliminated the time. Okay, so we can try again here. More trickery here, but I think we'd be happier trying to start with this version of x. So we're going to eliminate time, or solve for time in this equation. So we send the 2 over. Now we're going to need to square to get rid of the square root of t. And we've got something now that we can substitute into the other equation. We now have an equation that's about y and x, and it has eliminated the parametric time. Okay, so let's try another one. I think I'm going to start here. There are alternative answers, but I'm going to start with this. So obviously t is going to be the square root of x. That's all you got to do. If that's a valid substitution, we're going to put that into here, and we're going to get y equals the natural log of the square root of x. Okay, now let's do this with cosine and sine, with some trig functions. This is going to be trickier. I'm just going to show you what the trick is to this, and you'll be able to know it moving forward. So if I try to just set x equal to 4 cosine of t and try to solve for t, the only way I could do that is with an inverse cosine. So that would be difficult. It could be done. You could do that. But look at the trick. I'm going to say if x equals 4 cosine of t, couldn't I say that cosine of t is x over 4? Now, what's different about this one, I don't have anything that I can sub into the other equation, but watch this trick. They're going to do the same thing again. and use the other equation and find that sine of t is y over 3. Okay, well I've got these two statements, but what good does that do? I need some kind of equation to tie it all together. Well, look what they've done. They're going to use the Pythagorean identity and substitute in these two. Substitute cosine of t and sine of t into the Pythagorean identity. We didn't have an equation that unified them, and we just used this and kind of created it ourselves. This is a true statement. Cosine squared t plus sine squared of t is 1. So, and I know what cosine is and I know what sine is, so let's sub them in. So pretty clever trick that I don't think you would have thought of on your own, but once you see that trick, we create this. Now let's try it again here. So it's the same trick. So pause it if you want to try on your own, but I think you'll see. I'm going to solve both of them just for the trig function. Okay, now that's the best I can do. So how do I create an equation? Cosine t squared plus sine t squared is going to be 1, the Pythagorean identity. So this is what cosine of t is, so I'm going to sub it in. This is what sine t is, so I'm going to sub this in. I'm going to get x squared over 4 plus y squared over 9 equals 1. And I've created an equation that has eliminated the parametric aspect of time.